alkanes, and when you had two alkane molecules that want to stick together, and I can picture it in your textbook. They showed it down here where electrons were kind of scooting to one side over here, and then made it partially negative, partially positive over here, and then actually had another one that had a partially negative area, and then you kind of had a connection between those. Those were called London forces. They're not, they're a type of what we call intermolecular bond, but when it comes to water, water has something even more interesting. It's called hydrogen bonding. So if we look at a water molecule, the hydrogen atom is going to be partially positive, and the oxygen atom is going to be partially negative. So I've got some figures kind of coming up. I know there's only 3 of you, but help me out here. So I can remember Friday we were looking at this, so can you look back at your notes? And I'm going to ask you for hydrogen. Can you tell me oxygen's electronegativity value? No?
I don't have my notes.
Your notes?
But I wasn't here Friday.
You weren't here Friday?
3.5.
3.5? Well, we'll just ask Natalie for everything. So 3.5, that's electronegativity. What about hydrogens?
2.1.
2.1. And I've got a packet to give you or whatever if you want it. So, okay. So yeah, my point was going to be that with regard to this type of bond, I don't think you need your notes for this one. I'm going to pick on you, Autumn. So is this a covalent or an ionic bond right here? Between this right here, between this oxygen and this hydrogen, is that covalent or ionic?
Covalent.
It is covalent, perfect. We'll start there, awesome. And so in that bond, covalent bond, in that bond, Natalie, how many electrons are shared? Remember when we draw a Lewis structure, every time you see dash, that's how many electrons? 2. Perfect. And I don't have anything yet for you, Taylor, but it's kind of cool. So you're going to see this convention used, and remember the partial looks kind of like an S, like that. That means partial. And so we can have partially positive or partially negative. So up here for the 3.5 over the oxygen, I'm going to put partially negative. For the 2 hydrogens, I'm partially positive, partially positive. That's kind of a reminder. I think we talked a little bit about that. But what this is saying is, and this is how I learned it, if you find oxygen on the periodic table, on both sides of oxygen, we have nitrogen and fluorine. Bottom line is, if I take that oxygen atom and substitute it for either a nitrogen or fluorine, I'm still going to have this cool thing called hydrogen bonding that can go on. So hydrogen bonding is this. If you, by golly, have an oxygen and a hydrogen, or if you have a nitrogen and a hydrogen, or if you have a fluorine and a hydrogen, this is all where you can get hydrogen bonding. Everybody loves hydrogen bonding. In all of these cases, the hydrogen is going to be partially positive. And in all these cases, the nitrogen, oxygen, or fluorine is going to be partially negative. Okay? That's hydrogen bonding. So I know your textbook mentions it, but if you have dabbled in biology with the DNA and RNA, those strands, those molecules are humongous. And I'm kind of going like this because they kind of wrap around. But within that structure, they do have kind of a lot of this, the nitrogen, hydrogen regions of DNA allow for hydrogen bonding. Okay. So hydrogen bonds are what we call intermolecular bonds, and that covalent bond is intra. And if you're like me, I'm like intra, what the heck? But if you think of the term interstates, like the road, an interstate joins states, and kind of think of those states as being different molecules. So I'm going to kind of erase this because this is pretty busy. that. All it means is if we saddle up another water molecule, here's my other water molecule. This would be what? Partially negative, partially positive, partially positive. Hydrogen bond is just this. Basically, it connects a hydrogen of one molecule with the oxygen of another molecule. That is your hydrogen bond, and that is your what they call it? Intermolecular bond. Okay, that's it. So what I drew is up here. So what do you think, Taylor? I don't know if you're okay with color. Can you see two colors there? So kind of the pink. Which one is that? Is that hydrogen bond or is that a covalent bond? That is hydrogen. Yep. And so Autumn, what is the blue? Yeah. Covalent. Yep. You got it. And I don't think you're, in this part of the course anyway, emphasizes it as much as I think it is so cool. We must have talked about it earlier. This is, of course, liquid. And we know we could freeze it and get ice. And we know we could boil it and get a vapor. Here's the deal. If I kind of make my boxes, that's my solid, that's my liquid, and that's my gas. S for solid, L for liquid, G for gas. If I were to look at the particles in my liquid, I would see, here's my water particles. With regard to these hydrogen bondings, these intermolecular bonds, I would see just kind of a certain amount of, and I do have other colors, but I'm just going to kind of, just bear with me. I'm kind of connecting up a few of these. Okay, I'm just kind of connecting up a few. Gas, water gas, no connections, no intermolecular bonds, and this is not going to translate very well, but for my solid, I'm drawing dots to represent my water molecules, and I'm just drawing a mess of hydrogen bonds and mess of those intermolecular bonds. So if as I go from left to right, I'm getting less, I call them IM or intermolecular bonds. And here there are less hydrogen bonds. Okay, so that's kind of what we have going on. That's a big hairy. Okay, so I forgot who we left off with. Might be, I think I knew on them. I feel like we kind of said, so explain in your own words, maybe Autumn, a little more. What are the dashed lines? How do you think of them, the dashed lines in this figure?
The hydrogen bonds.
Yep, very good. So then on to you, Natalie. Let's see, in this figure, label two adjacent water molecules with, remember that means partially, if you see that S thing, that means partially positive, partially negative. So just help me out, Natalie. Let's pick on the middle H2O. So where would I put my partially on the oxygen and the hydrogen, my partially positive? I would put them on, all right, perfect. Partially positive. So why don't you guys go ahead and do that on yours. And then the oxygen gets partially negative. Cool. At least let's go ahead and do it in another one, at least one. Okay. So we're back to you, Taylor. We're going to knock out what NH3 looks like. Now, I'll just go ahead and tell you. NH3 looks like this. I have nitrogen in the middle. I'm going to do 3 covalent bonds, and I'm going to connect up my hydrogens. And then, what's that? There's 3. Oh, we need to draw 4. Yeah, you're right. But, so maybe a specific question, Taylor. So when it comes to this molecule, where am I going to put my partially positive, my partially negative? I can't hear you. Positive on the hydrogens, yep. And then partially negative on the nitrogen?
Yeah.
Okay. Cool. So I'll do it this way. I'm not gonna draw 4. I'm gonna draw 1 more down here, and then Autumn, help me write in a hydrogen bond, an intermolecular bond. Partially positive, my hydrogens, partially negative, my nitrogens. So help me draw just 1 at least.
So you draw a dotted line
Mm-hmm.
down to an N.
Yep, from
Yeah,
any of the H's. Yep, dot, dot, dot. Yep, that's it. That's totally it. Very good. And I don't want to like go shma. I mean, this right here, these dots we've been talking about, those intermolecular bonds, they're not as strong as, as these covalent bonds. So for instance, like if we were to boil that water, these guys would be broken. Some of them, or yeah, all of them are going to put in this gaseous state, okay? But not these guys. But they're pretty strong relative to other intermolecular bonds. So hydrogen bonds, like I said, are not as strong as the covalent bonds, okay? Looks like I tried to hide maybe the word properties. So water has some interesting properties that thank goodness it has. So let's see. Oh, I think Natalie. So if I've been talking about how strong these intermolecular bonds, these hydrogen bonds connecting the water molecules are, what do you think? It's going to boil at a high or low temperature? High, exactly. High boiling point temperature of water. Exactly. The word here is high surface tension, and I could have done this as a demo, but it's you'll see. Water, because the intermolecular bonds are so strong, they stick together really well. One of my favorite things I remember as a child, watching a stream, and you'd see those water bugs, those water bugs that can walk on the surface. You're like, wow, that's so cool. But that's actually because of one of the properties of water.
So when water's boiling, as long as it's in the water state, it's got hydrogen bonds, but it's when it evaporates off or it breaks them.
Right, yes, exactly. When it's a vapor, there's no hydrogen bonds. And when it's a solid, there's a lot more hydrogen bonds even than when it's a liquid. You got it. And so this is something you could do to amaze your friends. Oops. I kind of squeezed in there. Have you probably noticed we're coming up on spring? I'll put it this way, again, kind of growing up, or maybe even now, if you fill your swimming pool with water, and it's a nice sunny day, would you say that water heats up quickly or slowly? Slowly, me too. Me too. Everything when the sun's like banging it with energy, everything has it's called specific heat. Things like water are slow, they have high specific heats. They're slow to heat up. Other things like air, oh my gosh, air heats up just like that. You know that because like on a sunny day, if you go in the shade, it's cold, and if you go out, beyond the shade, your air is heating up just so quickly. It has a low specific heat. And that actually has consequences for the Earth. One of the things we're going to talk about is global warming, or we've been talking about it, not just look at it this way. If our, the oceans, the large bodies of water, act even bigger than our swimming pools, have been stubborn or a delay in those oceans heating up. Now, once those oceans are hot, kind of like your swimming pool, like you can go ahead and take a dip in at midnight in your swimming pool if it's nice and warm, because just like it's stubborn to heat up, it's stubborn to cool down. And that's what the oceans do. So that property of water actually has global consequences. So, okay. We talked about this maybe the other day, ice floats, and I know Glenda was saying, well, does it trap as it kind of fluffs out, as it transitions from a liquid to a solid, does it trap air in it? And the answer is yes. But I will also say, as a liquid, this actually has air trapped in it too. Air, oxygen, nitrogen, carbon dioxide. Okay. So porous is the word there. When water solidifies, it makes these little holes. It makes it porous. And I call it fluffing out. As it kind of assembles in its crystalline lattice structure, we really see kind of the crystalline lattice structure when we see snowflakes, right? Then it makes these holes, and so that means that for the density of a solid is less than the density for liquid. Density for a solid water is less. Liquid water is more dense. And that's actually unusual. So from your textbook, I had to go and double check what these substances are. This is paraffin, you know, like liquid paraffin. They must have had to heat this up, right? And solid paraffin is more dense than liquid paraffin. That's the way solids generally roll of the same substance. Solid is more dense, liquid is less dense. But for us, this is water, this is liquid water, and this is solid water. For us, solid water is less dense. So that's this quote. And again, if we go back to kind of impacting here, life as we know it, if you've ever seen the movie The Waterworld, okay, if our glaciers were more dense than the water they're floating on, the glacier would fall down like this, sink to the bottom, and it would displace the water that it fell into. That would be a bad thing. Plants and fish actually count on, well, I suppose, just off the top of my head, what do you think, why do fish care?
Because there's that ice layer on top which insulates the water.
Oh, yeah. The ice insulates the water here, keeps them a little warmer than they otherwise would be.
What keeps it from freezing solid?
Ah, the layer of ice keeps this from freezing solid. Mm-hmm. The other thing is, and that makes more sense, and the other silly thing is if our ice fell, then you'd have little issues swimming on top of the solid ice, which
and it would freeze solid.
Yeah, you're right. This helps it not freeze solid. Yep, exactly. Very fun. Let's see, who did we, let's pick on you, Taylor.
So is water the only thing with hydrogen bonding?
No. Nope. See anything,
right.
This right over here? Yeah, if you look at a molecule, and it can be a crazy simple molecule, for instance, NH3 that we looked up, NH3 has these NHs, and that means that you got hydrogen bonding capabilities. Yep. So anywhere in a molecule that's got those atoms joined together, you're going to have partially positive over the hydrogen, partially negative over the nitrogen, oxygen, or chlorine. So Taylor, are covalent bonds broken when water melts or boils? Covalent bonds? No. Explain. So put another way, in this mess of water molecules, which bonds are going to be broken, the dotted ones or the solid ones?
So you're asking me?
Yeah,
That's
that's what I'm
what
thinking
I
on
looked
table.
at.
Yeah, let's move on. Yeah,
The dotted ones?
The dotted ones are going to be broken. You told me the dotted ones are the intermolecular, the hydrogen bonds. The dotted intermolecular and hydrogen, intermolecular bonds, hydrogen bonds means the same thing. Cool. All right. So figure from your textbook, and you probably already knew this, but on the planet Earth, 97%, this just blows my mind, 97% of, I think this would be liquid, no, just water, because we solid water too. 97% of the water we have is in the oceans. They're like, are you serious? So on to you, Natalie. Only, what's the percentage here? Only blank of water is found on Earth is fresh water. 3%. Mike and 3, yep. And then Taylor, about blank of this fresh water is locked up in glaciers, ice caps, and snowfields. Yep, I put 69%. About 69% is, 69 of that 3%, are you serious? Okay, so Autumn, about blank is found underground and must be pumped to the surface for use. About 30%, yep. Goodness gracious, makes me thirsty. Okay, Natalie, lakes, rivers, and wetlands are only blank of the fresh water. 87%. Oh, 3%.
Wait,
Yeah.
lakes, rivers, and
Oh, yeah. I think, yeah, this little sliver is 0.3%. So of the fresh water, only 0.3% is, when I say surface water, that's the lakes, rivers, and wetlands.
oh,
Yeah. And you wouldn't know this, but, and I meant to bring, you know, how the 2-liter bottles, so you'll just have to picture it. If I had a 2-liter bottle here, the way this works out is that if that 2-liter bottle represented all the water on Earth, only 60 milliliters of it would be fresh water. And I'd ask you to guess, but I wouldn't know. Only 4 drops of that 2-liter bottle would be water that we easily have access to. I know, right? You know, when one of the things that I dabble in is astronomy, and to look at other planets, you're like, oh yeah, our planet's got water, our planet's got water. But when you start to look at how our water is distributed and where it's tied up, you're like, oh wow. Okay. So this is, I wish it went a little more current even. It goes every 5 years, it stops at 2010, and it's got 6 bars on there, 5 bars for each year, and they represent these up here. Now, one of the things I had to look up, and I guess I'll get to it. So currently we're looking at ballpark 355 billion gallons of water are withdrawn a day. 86% of that's fresh, 14% of that's salt. The word I hit up here is thermoelectric. And I had to look up thermoelectric. I'm like, what? Because the thermal part sounds like heat. So thermoelectric is where you burn things like coal and oil and things like that in your power in your electric plant. So you burn fossil fuels to create electricity. And I guess I never thought of it, but if you look at the thermoelectric power, check out how tall this is. Of our water uses, that's how much we use related to power. Like, how does that work? Well, it has to do with cooling down, the cooling within the plants. I mean, you compare that to public supply, that's the blue one. So who did I pick on that? Taylor, are you game? So Taylor, what's looking at 2010, the gold one is thermoelectric power, water, like I said, in the coal plants and stuff. What's the green one?
Irrigation.
It is irrigation. So those two, thermoelectric power and irrigation. And agriculture accounts for about 30%. I wouldn't have guessed it. I was like, is that really what it is? So if you find, and I didn't know if agriculture, they meant irrigation and rural domestic livestock, but the livestock really kind of surprised me too. And this, I'm like, are you serious? But I guess there's math to back this out. Oh, check this out. Have you ever heard of kind of different types of footprints? Like you have a carbon footprint, or we have a water footprint. So for every kilogram of corn we consume, you're looking at 1,200 liters of water that went into producing that 1 kilogram. It blows my mind.
Is the water footprint the difference?
What's that?
What is the water footprint?
Well, I'm gonna take us out to a website and I'll post it where you can like go online and click what you do. Your not food, but our water footprint would be like when we flush the toilet or when we do our dishes, when we do our laundry, when we drink. Those are like our water footprint. Okay. But these are, when we go to the store and buy a kilogram of corn, to get it to us in order for us to consume, it took that much water to grow it. It's just bizarre to me. 1 can of corn. Well, a kilogram might be multiple cans, I don't know, but not very many. Yeah, a couple cans of corn. And so I think we're up to you, Autumn. So this is one of your turns. How do crops and meat compare in this table? Meat is much higher than the eat crops. Oh, yep. Because then I have a follow-up question. Why is that? And Autumn said, that sounds really good. The meat is higher because the meat, actually, as an animal, as they're living, are consuming the crops. So that goes into their footprint. That's just amazing. Yeah. So here are some other things. A cup of coffee, which is about 250 milliliters, takes 260 liters of water. Makes me feel guilty. I just like.
I also read once, I don't know if it's like true, but that every time you drink a cup of coffee, the songbird dies.
The songbird dies?
Yeah, or something like that.
Oh.
It's like just in the, I don't know. And I had 2 this morning.
Feel guilty?
Yeah.
I do feel guilty.
Yeah.
I don't know if this is on the same topic, but did you, I thought it was on Facebook or something, I saw a video where in a supermarket in I don't know if it was UK or something, people were, they bought their food and then they had containers to put their food in and they left all the plastic there at the supermarket just to make a point for all of that plastic that our food is purchased. I find it all. Okay, so now, I don't know if there's a question there actually. You know, why are these numbers so ridiculously high and what can be done to reduce the amount of water used? Got any ideas?
They say not to eat meat products, like everybody wants to be vegan. However, I accidentally bought imitation cheese this weekend. Accidentally, it was.
No, not good. Yeah, our daughter's been vegan for not quite a year now, so.
Fake stuff is disgusting. Fake meat.
Yeah.
They have like vegan meat or whatever, like imitate meat.
Well, and you've got to be careful, I bet you are, that you get what you need from the plants, because there's stuff in the meat that I think
your body needs. So.
Yeah, some people can go without meat, but and also like
Protein and stuff. Yeah.
You can get it from beans and stuff, but iron is like.
But just one T-shirt, that's like liters of water, 2,500 liters.
But it's funny because, like, I know Leonardo DiCaprio is like so against beef because of probably stuff like this, and it's like, you have a yacht, like, right? And all my friends that are like cowboys and stuff, they have such a good outdoor life that I can use very.
Yeah, it's
Don't
different.
think about.
So here's that link. The water use calculator, and I won't like take you through, but it makes you think because like they ask you, do you have like low flow toilets or even your dishwasher. I mean that use, and I'm like, well, now do you use more or less water when you run a dishwasher? I don't know. So you ask how many people are in your household, then you'll ask about the showers, okay, low flow, and I didn't get through the whole thing, but it will give you how much water that you use. So I'll push that out there. Or your water footprint, which probably will not be good. Okay. All right. Part 3. Does she have the other part? So tomorrow for lab, I'm going to do what I've been doing and have a sheet for you to kind of fill out and put into your notebook, or however you want to do it, because you're going to be testing your water samples. Bring 2, and if you can't get 2, bring just 1. But yeah, interesting. All right. There we go. So still on the topic of water. Actually, I have a link. I think it's, what do we got there? I think it's like, is it 9 minutes or so? But on average, we generally use 100 gallons of water a day. So the number there is 3/4. Nearly 3/4 of the water that we use goes down our drains. This is actually a water table, so this is the aquifer they're talking about. Okay. There are other water tables that can be resourced, but this is the largest one. Normally, we just take for granted that we've got access to clean water. Clean water can be contaminated by, I have abandoned mines here, runoff from fertilized fields, poorly constructed landfills and septic tanks, and last but not least, household chemicals that end up poured down the drain or on the ground. So let's take a look at, this is not our feel-good moment, another feel-good moment here. Let's take a look at this video. It does have sound.